Have you ever looked at a report showing the percentages of different minerals in a rock sample, or the concentration of various pollutants in a water sample, or maybe even the breakdown of how much time you spend on different tasks each day? These kinds of data, where the parts add up to a fixed total, are called compositional data. They're incredibly common in fields like geology, environmental science, biology, and many others. But here's the twist. It's a big one. **** standard statistical methods you learned in school or online. The ones designed for numbers that can be anything positive or negative don't work correctly for compositional data. ***. Applying them can lead to misleading or even completely meaningless results. It's like trying to use a hammer to screw in a bolt. You might think you were making progress, but you're just damaging things. This issue isn't new. Smart folks figured it out decades ago, but the mistakes still pop up everywhere. Think about it this way. If you have a rock made of quartz, feldspar, and mica, and you measure their percentages, if the percentage of quartz goes up, the percentages of feldspar and mica must go down, because they all have to add up to 100%. This happens even if there is no actual geological process linking the decrease in mica to the increase in quartz. Standard statistics, particularly measures like correlation, can falsely suggest that mica and quartz are strongly negatively related just because of this mathematical constraint. This is known as spurious correlation. It's a major headache when you treat compositional data like regular numbers. Its core idea, the single principle that should guide how we handle compositional data, is that only the relative amounts of the components matter. It's not about how much quartz you have in absolute terms, but how much quartz you have relative to the feldspar and mica, or relative to any other component. If you double the amount of every component in your sample, the composition hasn't changed. A meaningful analysis should reflect this. Standard methods, which are based on absolute values, fail this fundamental test. So if standard methods are out, what's the alternative? The key is to shift our focus to the ratios between the components. Instead of looking at the percentage of quartz and the percentage of mica separately, we look at the ratio of quartz to mica. If you double both quartz and mica, their relative amount hasn't changed, and this is what compositional data analysis captures. Taking the logarithm of these ratios makes the math work nicely with standard statistical techniques designed for real numbers. These are called Lagratios. Imagine you have a three-part composition. Maybe the amounts of sand, silt, and clay in a soil sample. So a traditional way to visualize this is using a ternary diagram. A triangle where each corner represents 100% of one component. While these diagrams are great for showing the data, they can be misleading if you interpret them using the same intuition you'd apply to a standard scatter plot of two variables. Just like correlation, simply plotting the raw percentages on a ternary diagram can create apparent patterns or relationships that are just artifacts of the fact that the percentages must sum to 100%. Harker or Fenner diagrams, which are just scattergrams of two raw components, suffer from similar issues. The correct way to approach compositional data recognizes that they live in a special kind of mathematical space called the simplex. It's a geometric space where every point represents a valid composition. The simplex has its own geometry, different from the standard Euclidean space where regular real numbers live. Think of it like trying to measure distances on a curved surface versus a flat plane. You need different tools and rules. Compositional data analysis provides the right tools and rules for the simplex, largely based on the idea of Lagratios. Using Lagratios allows us to transform the compositional data from the simplex into a standard, real space where standard statistical methods can be applied correctly. This is the transformation methodology. Alternatively, some methods work directly within the simplex using operations appropriate for compositional data, which is sometimes called the staying-in-the-simplex methodology. Importantly, these different approaches lead to the same correct conclusions if applied properly. The choice often depends on what feels more intuitive to the analyst. Despite the existence of these sound methods, some common fallacies and confusions persist. One is stubbornly holding on to the idea of correlation between raw components. People might try to defend this by referring to traditional methods, but tradition doesn't magically make a flawed approach correct. Another fallacy is assuming that traditional diagrams like ternary plots used in a raw way are somehow superior to other visual methods, when not interpreted through the lens of compositional data principles. they are just as susceptible to showing spurious patterns as simple scattergrams of raw percentages. Another mistake can happen when researchers fall into the trap of data snooping. This is where you look at your data, first see a pattern, form a hypothesis based on that pattern, and then test that hypothesis using methods that are biased towards finding what you already saw. It's like looking at clouds and deciding one looks like a rabbit, then finding a rabbit in a picture and declaring it's proof that clouds are made of rabbits. Sound scientific method dictates formulating hypotheses before analyzing the data intended to test them. Even seemingly intuitive ideas can be tricky. For example, some attempts have been made to unclose or open compositional datasets, trying to imagine the data came from some underlying process where the parts did unsum to a constant. But this can just replace one awkward constraint with another. The focus should remain on the data as they are recorded, parts of a whole. For exploring compositional data, simple summary statistics like the arithmetic mean or standard deviation of raw components are nearly useless. The information is in the ratios. Instead, compositional data analysis introduces concepts like the compositional center, which represents a kind of average composition in the simplex geometry, and the variation matrix, which captures how the ratios between components vary. Graphical tools for compositional data should also respect their relative nature. Ratio scattergrams, Lagrangian scattergrams, and compositional biplets are examples of diagrams designed to visualize the relationships between parts correctly by focusing on their ratios. Let us look at a real-world example from geology. Analyzing the chemical composition of water samples from a river basin, the water contains different dissolved ions, and their concentrations can be viewed as components of a composition. Geologists might want to know if the water chemistry changes significantly as the river flows through different geological areas or is affected by human activity. Applying standard statistics directly to the raw concentrations in MgL would be problematic due to the compositional nature of the ion concentrations. For instance, comparing the average concentration of calcium in one section of the river to another using a standard t-test might be misleading. Instead, using compositional data analysis, researchers first recognize that the ion concentrations, when considered together, form a composition. After accounting for any unmeasured components like the water itself, although the analysis often focuses on the relative amounts of the measured ions, they can then use coda methods. For example, they could calculate the compositional center for water samples from different parts of the river basin, and compute adjacent distances between these centers to see how far apart the typical compositions are. This gives a meaningful measure of compositional difference that isn't distorted by the summing constraint. They could also use compositional biplets to visualize the relationships between the different ions and how samples from different locations cluster. A biplot can show, for example, that certain ions are related to anthropogenic activities, while others are linked to rock weathering, and that these two processes might be independent in terms of their relative contribution to the water chemistry. More specifically, they might use techniques like calculating balances, which are normalized Lagrangians of geometric means of groups of components. These balances can represent meaningful geochemical processes and can be used to differentiate water samples from different subbasins based on their chemical characteristics. Statistical tests designed for compositional data, it's often performed in the transformed Lagrangian space, can then confirm whether the differences observed between groups are statistically significant. Compositional data analysis isn't limited to geochemistry. It's used in archaeometry to study the composition of ancient artifacts, in ecology to analyze species abundance, in nutrition to study dietary intake of different food types, and even in analyzing how people spend their time. While the concepts might seem unfamiliar at first, particularly the idea of a different sample space in geometric operations, specialized software packages are available in statistical programming languages like R that make applying these methods much more practical. These packages provide the necessary functions for working with compositional data correctly, from calculating compositional means and distances to performing sophisticated multivariate analyses like principal component analysis on Lagrangians. In conclusion, if you're working with data that represents parts of a whole, whether it's the mineralogy of a rock, the chemistry of water, or anything else that sums to a constant, you need compositional data analysis. Ignoring the unique nature of this data type and applying standard statistical methods can lead to you down a path of spurious correlations and meaningless results. By embracing the principle that only relative amounts matter and using the tools provided by Coda, you can unlock the true insights hidden within your compositional data and ensure your conclusions are scientifically sound. It might require learning some new tricks, but it's definitely worth it to avoid falling into the statistical abyss. Original source: http://creativecommons.org/licenses/by/4.0.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 650 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 1,800 Earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.